Good morning. Today what we're going to do is we're going to continue our discussion on these double replacement or metathesis reactions. Today we're going to see what happens whenever you put a compound in water. Does it actually stay together or does it break apart? We're going to learn how to figure out whether it stays together or breaks apart and how we can indicate that using ionic equations and net ionic equations. All right, so here we have this idea of dissociation. And so we've mentioned dissociation before. We said that when you put an ionic compound in water, it has a tendency to break apart. So down in the picture at the bottom, we have sodium chloride. So there's little positives, which are your sodiums, and little negatives, which are your chlorides. And when water comes along, it can separate the sodium from the chloride, and they're each independently in the water. Not like whenever we had sugar. Sugar stays together. It's a molecule. The ionic compounds actually break apart. So we need to be able to say, okay, when you put, say, sodium chloride in water, how do we show that they will actually break apart? That's called dissociation. And I'm going to write a few of them on the next slide for you. So a couple of terms, AQ means aqueous or aqueous. That just means that it's dissolved in water. It's surrounded by water molecules. If we use water in particular, sometimes they'll use the term hydrated. We don't use that one too much, but occasionally you'll see it. And if you have a polyatomic ion, it's going to generally remain intact. So whenever you see like this little negative charge over here, instead of just being a chloride, it might actually be an entire polyatomic ion like nitrate or phosphate. So let's look to see what happens when we try to write these dissociation equations. All right, so let's write out a few of these dissociation equations. What happens when you put a compound into water? So if we look at sodium chloride, we know that sodium chloride will dissolve. It's an ionic compound. It also dissociates. It also breaks apart. So to write that, we would say, all right, we got sodium chloride, and when you put it in water, it breaks apart. It forms the sodium ion and the chloride ion. Now, as we start looking at this, you have to keep in mind what charges are. So that was like chapter 2 stuff. And we also have to keep everything balanced on both sides of that equation. So let's try another one. Let's try calcium chloride. Calcium chloride is CaCl2. And when we put this in water, it also dissociates, forms the calcium ion. Okay, what charge is calcium? Yep, it's a positive 2. We know that because it's in group 2A. And then we have these chlorides, and we have to figure out what happens to them. Now, it turns out that these chlorides, they get a negative charge. So they don't want to be together. They actually want to split from one another. So we'll have calcium goes in one spot, one chloride goes over here, the other chloride goes over here. So they're going to split from one another. Now, to show that, we put a big 2 out front. We have 2 individual chloride ions. One more example for you. Let's look at, okay, how would you name this one? Na2SO4. That one is sodium sulfate. With sodium sulfate, the first thing we're going to notice is we have sodium. There's 2 of them. Again, they split from one another. They're individual ions. So I'm going to say 2Na+. Now sulfate, remember just based on how we name it, it's actually a polyatomic ion. And so polyatomic ions like to remain intact, meaning that it wants to stay as SO4. That part doesn't want to break up. So I'm going to write SO4. Remember, sulfate means it has a sulfur and 4 oxygen, and that has a negative 2 charge. All right, so we've balanced each of the individual elements. We've balanced the charges. Everything looks good. Well, let's see what else we're going to do next. What we get to focus on is being able to write equations, these reactions in different ways. And there's a lot of different ways that we can do that. So we can write what's called a molecular equation. And this is what you're familiar with so far, where we write the species, the whole chemical compound on the reactant and the product side. So it says all species are written together. We're not doing the dissociation that you just saw. But this doesn't necessarily describe what actually takes place in solution. So say you put sodium chloride in water, that sodium and chloride split from one another and they move independently of one another. But when we write NaCl, it doesn't really give you that sense of what's going on whenever it's actually in water. So ionic equations, anything that's a strong soluble electrolyte, we break apart. We write it in what's called the dissociated form. This gives a better indication of what actually takes place. So this is like did you ever watch Magic School Bus? So if we could get in the Magic School Bus and we could go down into the solution, we could see that these ions are actually separated from one another and they're moving independently. And that can give us a better idea of figuring out whether or not something's likely to react. So molecular is like what we've always been doing. Ionic, anything that's a strong soluble electrolyte, gets broke apart. Now, we're not quite done yet. Let's see what else we could do. Now, one of the things that we're going to see is that during a chemical reaction, sometimes there's things that just sit there in that solution, especially when we're able to take the ionic equation where we can see the individual ions. Some of those ions don't actually react. They're just spectators. It's kind of like you go to a sports event and the spectators are the ones that sit there. I mean, yeah, they can cheer and they can give you energy and everything, but they don't actually participate. They're not on the field. So we have what are called spectator ions. These are ions that do not actually take place in the reaction. They're there before the reaction, they're there after the reaction, and they're in this ionic form the entire time. If we remove those spectator ions, because again, they're not an important part of the reaction, we end up with what's called the net ionic reaction, net ionic. The net ionic shows us the parts that actually react. This allows us to generalize, so I can say, oh, if I can grab something with this ion, and if I put those two compounds together, I'm likely to form a solid. On this, again, we still have to keep the number of atoms and the charges balanced on both sides. That part never, ever goes away. So by now you're like, I don't know what you're even talking about, Miss Lumley. Let's try a few examples and we'll see if we can kind of make this a little bit easier. All right, so here is a reaction where we want to write out the ionic and net ionic equations. What you see at the top is the molecular equation. All of the species are written together. This is what we normally see. So let's look at this one. Okay, what is that first compound? COCl2. COCl2. Wow, can't talk this morning. That would be cobalt chloride. In particular, it's actually cobalt 2 chloride because cobalt is a transitional metal. If it reacts with two sodium hydroxides, it forms cobalt 2 hydroxide and two sodium chlorides. If you notice, we've written the phases of each of them on there. Now here's a general rule of thumb. If it says AQ, we're going to assume that it can break apart, that it can dissociate. Now we're going to find out that weak acids and bases don't do that, but that's not in today's lecture. So for today, anything that says AQ, we're going to break apart. So that first one, cobalt chloride, it breaks apart. So let's see here, let's write it down. We have CO. Now we said that this was cobalt 2, meaning that it has a positive 2 charge. If you don't remember for sure, we'll just look to see what it's attached to. In this case, we have two chlorides. Each of those chlorides have a -1 charge. So cobalt has to have a positive 2 charge to make it balance. Now we have Cl2. The two chlorides will split from one another. We'll have independent little negative charges there. I have sodium hydroxide. Now notice there's a big 2 out in front. That means that I have 2 sodium ions. And I have 2 hydroxide ions. On the product side, well, the first thing that's listed is this cobalt hydroxide. Notice it says solid after it. Solid means that it does not split apart when you put it in water. It's actually forming a solid. So we leave that together. COOH2, and I'm going to go ahead and put that little S down there. Now down here at the end, I have 2 NaCl. Yes, it splits apart because there's an AQ after it. Now I'm kind of running out of room, so I'm going to write this just right underneath. 2Na plus 2Cl minus. I had to put the 2 because there was a coefficient of 2 out front. Now I'm going to look at this and I'm going to see exactly what's the same on both sides of the equation. So cobalt is by itself on one side and it's in a compound on one side. So that's not exactly the same. Now the Cl's are though. I have 2Cl minus, 2Cl minus. The sodiums are also exactly the same. Now those things, the things that are exactly the same on both sides, we call those spectator ions. So in this case, my Na plus and my Cl minus are the spectator ions. Those are the ones that they kind of watch what's going on, but they don't actually participate. Anything else that I have written, I'm going to rewrite for the net ionic. So what I just finished writing is the ionic equation. And so now let's work on the net ionic. So the net ionic will be cobalt with its positive 2 charge and 2 hydroxides with their negative 1. And when they come together, they form cobalt hydroxide, which is a solid. Now, one other little note. Technically, I should be writing AQ after everything I split apart. But I tend to be a little bit lazy, and you'll see that that happens a lot. So just make sure that if it's not AQ, if it's anything else, if it's a liquid or if it's a solid, you make sure to indicate that on every line after it. But yeah, you kind of get a drop the AQ. You're not supposed to, but I won't get onto you for that one. So how do we know what way we're supposed to write the equations? Is any of them actually better than anything else? Well, each way that we've written that equation, the molecular, the ionic, and the net ionic, they each have their own purpose. The molecular is great for planning an experiment and performing stoichiometry. It's a lot easier for the stoichiometry if you go back to the molecular. And also, if I'm going to go into the lab and I'm going to set up this experiment, it makes it a lot easier for me because I know exactly what compounds to grab off of the shelf. Ionic, that one actually gives us a better indication of what's actually taking place on the molecular level. So to know that idea that some of your compounds are going to split apart and you're going to have ions that are just sitting in solution, they're able to flow freely, then they're more likely to react. So later on when you learn about kinetics and equilibrium, that's going to be very helpful for that part. Net ionic focuses on the actual chemical change that takes place, allows us to generalize. Oh, I know if I have something with cobalt and I have something with hydroxide, it's going to make this solid at the end. So each way has their own advantages and disadvantages, but I promise you on your next test, you're going to have to be able to write all three. So get familiar with all three of them.